Welcome to our deep dive into the foundational principles that ensure data reliability and integrity in database systems, the ACID properties. In an increasingly data-driven world, where millions of transactions occur every second, from banking transfers to online purchases, the consistency and accuracy of information are paramount. Imagine a scenario where a banking transaction partially completes, leaving your account debited but the recipient's account not credited. Such inconsistencies could lead to catastrophic errors and a complete breakdown of trust. This is precisely where ACID properties come into play. They are a set of 4 critical characteristics: atomicity, consistency, isolation, and durability, forming a bedrock for reliable transaction processing. Developed in the late 1970s, these principles have become the gold standard for relational database management systems, guaranteeing that data remains valid even amidst system failures or concurrent operations. Understanding ACID is crucial for anyone working with databases, ensuring the integrity and reliability of their applications. Let's begin with atomicity, the A in ACID, which embodies the all-or-nothing principle for database transactions. This means that a transaction is treated as a single, indivisible unit of work. Either all operations within the transaction are successfully completed and committed to the database, or if any part of the transaction fails, the entire transaction is aborted, and the database is rolled back to its state before the transaction began. There are no halfway measures with atomicity. Consider a typical bank transfer. Money must be debited from one account and credited to another. If the debit succeeds but the credit fails, the transaction must be entirely reversed to prevent data inconsistency. The system ensures that the transfer never leaves the database in a state where money is lost or created out of thin air. This property is fundamental in guaranteeing that complex operations maintain data integrity, preventing partial updates that could corrupt the database's state. Next, we delve into consistency, the C in ACID. This property ensures that a transaction brings the database from one valid state to another, preserving all defined rules and constraints. It's about maintaining data integrity and adhering to predefined business rules. These rules can include things like unique keys, foreign key constraints, or even more complex application-level validations, such as an account balance cannot be negative, or the total number of items in stock cannot exceed warehouse capacity. If a transaction attempts to violate any of these rules, the database system will prevent it from committing. For instance, if a rule states that a product's price must always be positive, any transaction attempting to set a price of 0 or a negative value will be rejected. Consistency guarantees that the data always remains in a correct and meaningful state, never allowing the database to enter a corrupted or illegal configuration. It's the gatekeeper of your database's logical correctness. Moving on to isolation, the I in ACID, which addresses the challenge of concurrent operations in a multi-user environment. Isolation ensures that multiple transactions executing concurrently appear to be running sequentially without interfering with each other. This means that even if several users are accessing and modifying the same data simultaneously, each transaction's intermediate state remains invisible to other transactions. It's like having multiple people working on separate copies of a document and then merging their changes flawlessly at the end. Without isolation, issues like dirty reads, non-repeatable reads, and phantom reads could occur, leading to incorrect data or lost updates. Imagine 2 users simultaneously trying to buy the last item in stock. Isolation ensures that only one transaction successfully allocates that item while the other is properly handled, perhaps by indicating the item is out of stock. Various isolation levels exist, such as read uncommitted, read committed, repeatable read, and serializable, offering different trade-offs between concurrency and strictness. The goal is to provide a consistent view of the database to each transaction, regardless of other ongoing operations. Finally, we arrive at durability, the D in ACID, which guarantees that once a transaction has been successfully committed, its changes are permanent and will survive any subsequent system failures. This means that even if the database system crashes immediately after a commit, Due to a power outage, software error, or hardware malfunction, the data will not be lost. The committed changes are persistently stored and can be recovered when the system restarts. To achieve durability, databases typically write transaction logs to non-volatile storage, like hard drives or solid-state drives, before acknowledging the commit to the application. These logs can then be used to reconstruct the database state during recovery. Imagine completing an online purchase. Once you receive confirmation, durability ensures that even if the e-commerce server goes down seconds later, your order and payment details are safe and will be there when the system comes back online. This property is absolutely vital for business continuity and user trust, as it guarantees that once something is recorded, it stays recorded, irrespective of unforeseen technical disruptions. Now that we've explored each of the ACID properties individually, let's understand their collective real-world impact. Why are these principles so important? The primary reason is trust and reliability. In critical applications, any loss or corruption of data can have severe consequences, not just financial, but also reputational and legal. Think about the financial industry. Every bank transfer, every stock trade, every credit card transaction absolutely relies on ACID properties to ensure that funds are correctly moved and recorded, preventing discrepancies that could cost millions. In healthcare, patient records must be updated with atomicity, consistency, isolation, and durability to ensure doctors have access to the correct, up-to-date information, potentially saving lives. E-commerce platforms similarly depend on ACID to manage inventory, process payments, and fulfill orders accurately. Without ACID, database systems would be chaotic, unreliable, and prone to errors, making it impossible to build dependable applications that handle sensitive information or high-value transactions. They are the invisible guardians of data integrity in our digital world. While ACID principles are the cornerstone of relational databases, it's important to acknowledge that not all database systems strictly adhere to them, especially in the world of NoSQL. This brings us to a brief discussion of BASE, an acronym for Basically Available, Soft State, Eventually Consistent. BASE represents a different paradigm, often favored by distributed NoSQL databases designed for massive scale and high availability, where absolute immediate consistency might be sacrificed for performance and availability. With BASE, data consistency might not be instantaneous across all nodes, but it will eventually reach a consistent state. This is a trade-off. For applications where eventual consistency is acceptable, like social media feeds or certain analytics systems, BASE offers advantages in scalability and fault tolerance. However, for applications demanding strict data integrity and immediate consistency, such as financial systems, ACID remains indispensable. Understanding this distinction is crucial for choosing the right database technology for your specific application requirements, balancing the need for strong consistency with the demands of scale and availability. How do database management systems actually achieve these powerful ACID properties? It's through a combination of sophisticated mechanisms and techniques. For atomicity and durability, the database relies heavily on transaction logging, often called a write-ahead log. Before any change is written to the actual data files, it's first recorded in a durable log. If a crash occurs, this log can be replayed to either commit incomplete transactions, redo operations, or roll back uncompleted ones, undo operations, ensuring atomicity and durability. Isolation is typically achieved using concurrency control mechanisms, primarily locking. When a transaction accesses data, it might acquire a lock, preventing other transactions from modifying or sometimes even reading that data until the first transaction completes. Different types of locks and isolation levels, like shared locks for reads and exclusive locks for writes, manage this delicate balance. Finally, consistency is enforced through schema definitions, constraints like primary keys, foreign keys, unique constraints, triggers, and application-level validation logic. Together, these internal workings ensure that the database consistently adheres to the ACID principles, providing a reliable foundation for data operations. While ACID properties are incredibly valuable, implementing and maintaining them isn't without its challenges. One significant consideration is performance overhead. Strict adherence to ACID, especially isolation, often involves locking mechanisms that can reduce concurrency. This means that if many transactions are trying to access the same data simultaneously, some might have to wait, potentially slowing down the overall system performance. This overhead becomes particularly pronounced in highly distributed systems, where achieving global atomicity and consistency across multiple geographically dispersed databases introduces significant complexity and latency. Imagine coordinating a single transaction across servers located on different continents. Ensuring all or nothing with strict consistency becomes a massive engineering challenge. Therefore, developers and architects must carefully consider the trade-offs. For applications that prioritize maximum availability and high throughput over immediate strict consistency for every operation, sometimes relaxing certain ACID properties or opting for eventually consistent models might be a more practical solution. It's about finding the right balance for your specific use case. In conclusion, the ACID properties, atomicity, consistency, isolation, and durability represent a cornerstone of reliable database management, particularly for relational systems. They provide a robust framework for ensuring data integrity, preventing corruption, and maintaining the accuracy of information, even in the face of concurrent operations and unexpected system failures. While the evolving landscape of database technologies, especially with the rise of NoSQL and distributed systems, has introduced alternative consistency models like Base, the fundamental principles of ACID remain incredibly relevant. For applications where data accuracy, transaction reliability, and strict integrity are non-negotiable, such as financial services, healthcare, and critical enterprise systems, ACID-compliant databases are still the preferred choice. As technology continues to advance, we're also seeing the emergence of hybrid database solutions that attempt to combine the best of both worlds, offering configurable consistency levels. Understanding ACID properties is not just about appreciating database theory. It's about making informed architectural decisions that safeguard the most valuable asset of any organization, its data. Thank you for joining us on this deep dive into ACID properties.